let's look at a few more interesting op-amp circuit applications. As I said before, there's a huge variety of different types of circuits you can build with op-amps. So let's just kind of look at just a few to kind of get a feel for some of the interesting little tricks and techniques you can use with them. So here, let's look at a circuit called a summing amplifier. And I want to point out, first of all, a couple of little shortcuts here. Okay? Note, I've got V1, V2, and Vn connected to these resistors. This looks very similar to an inverting amplifier, but we note in this case that I'm not actually bothering to draw the sources. And once again, this is kind of a convention you will see in circuit schematics. When you simply see a voltage represented on one side, especially basically on the left side of the schematic, that usually represents a source that is generating these voltages, which is not shown. So there is input sources that are not drawn. So once again, this is a simple shortcut. You see this used a great deal. Now the interesting part is on the right side of the schematic, these are normally outputs, so when I draw VO here, that doesn't represent a source. That simply represents the voltage of that node. So on the left side, there are sources generating those voltages. On the right side, that's simply an output. A little bit confusing, absolutely. But on the other hand, it's convention that people use throughout industry. So you will see this in a lot of books where you will not see the input sources on the left-hand side drawn, and then you will see a voltage on the right-hand side that simply represents an output voltage. Once again, all voltages are referenced with respect to ground. Okay? So, let's go through and let's analyze this circuit. Now notice, I've got any number of inputs and input source voltages that I care to have for this circuit. So I've got R1, R2, all the way through R sub n. I could have as many as I want. If I had just a single source, that would be nothing more than an inverting amplifier. But now I've got multiple sources. So now what does this act like? Well, let's go through. Let's first of all apply the three rules. My input currents must be equal to 0. I've got a virtual ground. And now let's go and pick some current directions through these N input resistors. Really, the only place I can write a Kcl equation is here at the inverting input node. And so in this case, what I've got is that V1 minus 0 over R1 plus V2 minus 0 over R2 all the way through V sub n minus 0 over R sub n. All of those must sum together and be equal to 0 minus VO over RF. And if I take this equation in rearranged terms, what I will get is the following. That VO is equal to minus RF R1 over V1 minus RF over R2 times V2 all the way to minus R sub n, pardon me, RF over R sub n times V sub n. So notice what I have here now. I've got a circuit that adds together each of the input voltages, and each input voltage has its own gain factor, its own gain term. In fact, if all of these resistors are the same, if I set R1 equal R2 equal all the way to R sub n and make them equal to some resistor R, then V sub O will just be equal to minus RF over R times the sum of all of the input voltages. So in other words, just equal to minus RF over R1 times V1 plus V2 all the way to V sub n. And so here you can see a circuit where we are just adding all the voltages together, and in this case just multiplying them by the same gain constant, by the same closed loop gain. So this is a summing amplifier. It both sums those input voltages and also multiplies them by a gain constant. This is basically a circuit that's doing math. It's doing algebra for you. It is summing together voltages for you. So before we had inverting and non-inverting amplifiers that would multiply an input voltage by a gain constant. This one not only does that, it now also can add together those voltages. Now there is a very common application for this particular type of circuit. Let's say we took a circuit like this, and let's say I made each of these input resistors variable. So I'm going to draw something here. What if I made these resistors variable? And I'm going to draw an arrow through each one to indicate that that is a resistor that you can turn a knob. You can vary the value of the resistor. Now, if I had a knob I could turn, I could individually set the gain for each one of those input voltages. I could change the gain magnitude individually. What application could we use this for? Well, one obvious application, if you're a musician, you've ever gone through and operated a mixer board where you have multiple tracks. So for example, this is vocals, this is an instrument, this is another instrument. Then you sum them together and then output a single track. That's what you're doing. So a summing amplifier has an application, among many others, in the music industry for doing things like mixer boards. So you see this kind of circuit used all the time in a lot of interesting little applications. Okay, so that's one possible use, a mixer board. What other kinds of interesting circuits can we do besides a summing amplifier? Well, let's look at a couple of those. Here is another interesting little circuit that once again allows us to do some interesting algebra on input voltages, two different input voltages. Let's look at this. What if I had a circuit like this? So I've got two voltages, VA and V sub B. So once again, the input sources are implied, but they're just not shown. Okay, once again, let's go through and let's solve for this in terms of the output, in terms of VA and VB. Once again, I'm going to apply the three rules. I've got negative feedback. If this is an ideal op amp, then my input currents are equal to 0. Now, I know that I have a virtual short circuit between these two, but I just don't know what the voltage is at the inverting and non-inverting inputs. So all I know is I've got some voltage V sub P at the inverting and non-inverting input, and I also know that Vn at the inverting input must be equal to V sub P. I know that has to be true. So let's go through and let's pick some current directions. And in this case, I've actually got two nodes that I can write Kcl equations for, both the inverting and the non-inverting nodes. So let's go through and do that. So for my Kcl, I've got VA minus VP divided by R3 must be equal to VP over R4. Of course, the current into the op amp is 0, so just this current's equal to that current for the VP node. And what I get then is that VP is equal to R4 over R3 plus R4 times VA. This is really nothing more than a voltage divider when you think about it, right? Just voltage division. VP is the voltage division of VA. Then I've got the VN node, and for that, I've got that VB minus VP over R1, knowing that VN is equal to VP, must be equal to VP minus V0 over R2. So I've got my two Kcl equations for the two nodes. Now I can go and I can substitute for VP. So I can substitute this term into those equations. And then I can go through and do quite a bit of algebra. And I'm not going to bother to go through all of those steps. But if I substitute for VP, and then I solve this, what I'm going to get is the following. If I solve for V0, what I will get is this. VO is equal to R1 plus R2 times R4 divided by R1 times R3 plus R4 times VA minus R2 over R1 times VB. So I went through just a lot of messy algebra to get from here to here. I've just skipped those steps, but this is what we'll get if we do slog through the algebra. Now you look at that, this doesn't look particularly interesting. So what is interesting about this circuit? Well, let's make an assumption. Let's assume that we choose resistor values. So if we choose resistors, and of course we can do that, right? We can select any values of resistors we want. If we choose resistors such that R4 over R3 is equal to R2 over R1. In other words, if we choose resistors so that the ratio of these two resistors is equal to the ratio of those two resistors, something very nice happens to this part of the expression. And once again, if we go through and substitute R4 over R3 and go through some algebra, we can show the following. In this case, VO will be equal to R2 over R1 times VA minus VB. Now what do we have? We have a circuit where we have an output that's equal to a closed loop gain multiplied by the difference, not the sum, the difference between two voltages. And in fact, we call this a difference amplifier. So once again, we can do some pretty interesting stuff here in terms of manipulation of input voltages. We can do all kinds of algebra. Later on, once we start looking at inductors and capacitors, I'll show you how we can actually do calculus. We can actually do derivatives and integrals of input voltages. Okay? So we've looked at all kinds of different amplifier topologies. Let's look at some other interesting circuits you can do. Here's an interesting circuit. Okay, let's look at what this circuit does. Now you take one quick look at it, it looks kind of like it might be a non-inverting amplifier, but this actually is used for a different function. In this case we've got VCS, which means we've got VCS as the voltage at the non-inverting input. We have negative feedback, input currents are equal to 0. If I've got VCS here, I've got it there, which means this voltage must be equal to VCS. All right. Now, I've got a load resistor, R sub L, here. I've got a current I sub L flowing through that load resistor. I'm going to define that current. Clearly, I sub L must also be the current through this resistor too, because I know that that current must be equal to 0. And therefore, I sub L is equal to VCS over RCS. So the current in the load resistor is independent of RL. So I have a current that flows through this resistor, which is independent of the resistance itself. What kind of circuit is this? Well, you can consider this to be a current source, right? This op-amp is sourcing a current through that resistor, and that current is a value that is set by this resistor, but not by the load resistor. So as far as the R sub L is concerned, it's connected to a current source with a current I sub L. And so this is a way of making a current source. Usually people kind of have trouble thinking, how would you make a current source with real circuits? Voltage sources are easy. Batteries, you can think of a battery as a voltage source. But a current source, well, you can do something like that. Create something that generates a constant current through a resistance of any value. You can do it with op-amps. So, one interesting example, and there are lots of different variations on how to build current source circuits like this. Let's look at another interesting circuit. And this shows you a really interesting application you can do with an op-amp. Let us say we had this op-amp circuit. Now notice we have negative feedback, so the 3 rules are going to apply. The interesting application of this comes about when we look at this circuit and we ask ourselves a question. What is the equivalent resistance between the inverting input and ground? That's a very good question. What is that equivalent resistance? Well, if we look at this, we say, how would we find the equivalent resistance between 2 nodes? We know how to do that. Thevenin's theorem. We can use that. We can use a source driving technique. Now, how do I know I can do that? Because what is a dependent current source? What is an op-amp? An op-amp is essentially nothing more, as we said before, than a dependent current source. That's really all that it is. Which means we can treat the op amp as a dependent source, which means I can use source driving to find REQ. So in this case, what I'm going to do is the following. I'm going to put a 1-volt source between the inverting input and ground. And according to source driving, I need to measure I sub t in order to find the equivalent resistance between those two nodes. So we look at this. Let's apply our 3 rules of op-amp analysis. I know that this current's equal to 0, that current is equal to 0. I also know that I've got 1 volt at the inverting input. Pardon me, at the non-inverting input, which means I've also got 1 volt at the inverting input due to the virtual short circuit. And now that I've got that, I've got IT flowing in here. If that current is 0, then that current must be IT as well. Okay? Let's go ahead and let's analyze this. So looking at this, I've got an output voltage V sub O. And so looking at this, all right, I can write a Kcl equation for this node. So VO minus 1 over RF must be equal to 1 over R1, which means that VO will just be equal to 1 plus RF over R1 multiplied by just 1 volt if we go through. So this is really nothing more, when you think about it, than the non-inverting amplifier equation. So that tells us what VO is. So once we know that, what is IT? IT must be equal to, in this case, 1 minus 1 plus RF over R1 divided by R2. And if we simplify this, 1 minus 1 is going to cancel, and what we're going to get is IT is equal to minus RF over R1, R2. And now, what is the equivalent resistance between these two nodes? Well, the Thevenin resistance, which is equal to the equivalent resistance, is just equal to VT over IT. VT was 1 volt, and therefore this is equal to minus R1, R2 over RF. I've got an equivalent resistance which has a negative number. I mentioned before, can we have a Thevenin equivalent resistance that's negative? Absolutely. And this is how you do it. An op-amp is one way of doing that. So this is a negative resistance circuit. And you will see circuits like this applied, where you literally just take the input of this op-amp and connect it to some node, and that node will see a negative, effectively a negative resistance connected to it. So there are a lot of interesting signal processing applications, and also circuits like oscillators where this kind of technique is used. So once again, thousands of different possible op-amp circuits. This only shows a tiny fraction, but this kind of gives you an idea of the versatility of the kinds of tricks you can do with op-amps. And you can go on the web and find, websites where literally you can just type in some type of application you wanted to build with an op-amp circuit, and then you can go and build it. And that's what makes op-amps so powerful, is you can go right into a lab, take a little proto board or a little breadboard, stick an op amp in it, connect up the circuit, and literally within 5 or 10 minutes have a working circuit. So that's what makes them very powerful, very versatile. And in fact, when you go on and take other courses in circuits, some of the very first things you will build will be circuits you make with op amps. So this kind of touches on it. I just want to say that you could teach an entire class in op amps, but that's kind of beyond the scope of this introductory circuits course. But in more advanced classes, you could literally spend an entire semester just looking at different techniques and applications of op amps. Pretty neat stuff. Okay, so next time let's expand on op amps a little bit more. Everything we've done so far has been with a single op amp. What would happen if we design a circuit that has multiple op amps in it? Well, let's look at some applications for that next time.